Okay, so, okay, great, thank you. Yeah. So, okay, so it was a wonderful discussion of dark matter. In fact, I mean, what we know about dark matter in the previous talk. So I'm going to skip part of what I intended to say, but just maybe review the major points of what has been said already. Okay. So I'm going to outline again this dark matter problem, okay, but this will come from a somewhat different perspective, so it will be coming from the perspective of experiments that can be done on the surface of the Earth or in space. Okay, so the focus is going to be on what dark matter could do in our own galaxy. Okay, then I'm going to update on this search for topological dark matter with GPS that we currently are conducting. Then I'm going to switch topics and I'm going to talk about a different model of dark matter. These are non-interacting bosons, and I'm going to talk about correlation functions of these fields, and I'm going to also derive the profile of the expected signal, which encodes all the dark matter priors, including the virial distribution of velocities, galactic motion, coherence time, and coherence length. Everything is going to be there. And then I'm going to talk about some experimental proposals. So at this point, some of this stuff is not worked out in full detail. So some of these are just at the idea stage. Okay, but at the same time, I hope that it will provide some motivation for our experimental friends to think about this in more details. Okay, so we already have heard that dark matter is 5 times more abundant, and one of the arguments that I hear, I mean, look at us, the baryonic matter, right? So, and how complex we are, right? Okay. Well, dark matter is 5 times more abundant, so it could be 5 times as more complex, in fact, right? So, and
or less.
Huh?
Or less.
Okay. Anyway, so it is a philosophical argument, right? So, but the thing is that there are many models of dark matter, and it's, I mean, of particular interest to our community are the models that atomic physics tools can test, the precision measurement tools can test. Okay, so. All right, so okay, and we already seen all these examples of how it is proved that the dark matter exists, and the important point also made by the previous speaker is that all of these observations are inferred from gravitational interaction of dark matter with luminous matter. Okay. And moreover, these observations are done on galactic scale. So, in fact, if you are building a dark matter model that you you try to figure out what dark matter is on a microscopic scale, essentially what you are doing, you are extrapolating from this 1 kiloparsec or 10 kiloparsec scales to laboratory scale. Okay. So, and of course, I mean, it's a huge extrapolation scale, okay? So, many orders of magnitude and many things can fit, right? So, and another thing, if you also, I mean, the gravitational interaction is a given, right? So, now if you try to make this dark matter particle or whatever it is to interact with your device, you have to come up with some additional interaction, okay? So, non-gravitational interactions. And it's also a challenge, and a lot of things can fit. Okay, so and in the past 2-3 years, I mean, our community has started this quest for a search of ultralight dark matter, and in fact, people are looking at different couplings. Okay, so But of course, I mean, if you are looking for a certain coupling, you have to search in a parameter space that hasn't been constrained yet. Okay, so that is one of the things that that is happening in that community. Okay, now, so okay, we don't know much about dark matter, but what is it that we do know? Okay, so and again, I am interested in what is happening in our own galaxy, right? So and this is our galaxy, the Milky Way. So we are somewhere here. Okay, so and so the galaxy is a spiral galaxy. It spins around, right? So and in fact we are going. The galaxy itself is embedded in dark matter halo. Okay, so this cloud here is a dark matter halo. Okay, so it sits in its own inertial reference frame. Okay, so I will refer to this reference frame as a galactic reference frame, and we are flying through this cloud at about 600 kilometers per second. Okay, so and this speed is actually quite large, right? But at the same time, it is still 1,000 times smaller than the speed of light. Okay, so in this reference frame, in the galactic reference frame, the velocity distribution of dark matter objects is nearly quasi-Maxwellian. Okay, so and also a typical velocity distribution. It has a spread of this of so-called virial velocity, and it's also about 300 kilometers per second. So the picture is as follows, right? It's like in this room you have gas, okay? There is this distribution of velocities in this room, of molecules, and then on top of that, I'm flying through this, that's 300 kilometers per second, okay? So this is the picture. Okay, so the energy density is this number, so it roughly corresponds to about one proton or one hydrogen atom per about 3-4 cubic centimeters. Okay, so in fact this is a huge energy density. Okay, so if you were to think about energy stored in a capacitor, okay, so it's much larger than this. Okay, so this number is much larger than the energy stored in, say, in a cubic centimeter in a capacitor. Okay, so it's just we don't couple to this energy density that well, and this is the question, right?
Excuse me, Andrei?
Yes.
So I thought that galactic formation models indicated that the dark matter within the plane of the galaxy spins up with the rotation of the galaxy. Is that accounted for?
So I talked to several cosmologists. Actually, I was on sabbatical here a couple of years ago, and I talked to several people. And yeah, there is some speed, but it can be neglected. At the level of 300 kilometers per second, this is a really minor issue. So now, okay, with respect to the candidates, okay, so I'm going to talk about two things. Okay, so so you could have these non-interacting fields. Okay, so essentially bosonic fields, and they could have very huge wavelengths. Okay, so and I mean my personal interests are atomic clocks. Okay, that's why I put an atomic clock here. Okay, so and the fields are going to oscillate at the Compton wavelengths of these fields, and oscillations at the Compton wavelengths are going to pull on the frequency of the clock transition, and then you could see spectral features at that frequency. Okay, so and now if you start talking about self-interacting fields, okay, you could form topological defects, or your dark matter could clump, and all of that, and then suddenly you have a situation when you have these clumps of dark matter, and then you could have an atomic clock that flies through, and if the fundamental constants change inside of those clumps, then basically you could just look at your clock and see if you are inside of the clump or not, right? So, and the masses are ultralight, okay, so, and the requirement on this range of masses comes from so it's 10 to the minus 24 eV comes from the requirement that the Compton wavelength of your particle is much smaller than the size of the smallest galaxy, okay? So, and 1 eV.
For the non-interacting field, sorry, is it essential that they are non-interacting or it's weakly interacting? Because I'm wondering how they would thermalize after they.
So they don't, in fact. Okay, so okay, so I will take extra time, right? Okay. Okay. So the thing is that of course, I mean, all of these guys they have energy density associated with them, right? So and if they have energy density associated with them, then Einstein tells us that according to general relativity, they have to interact at least gravitation. Okay, and this is given, right? Now then there is a question of thermalization of these objects. Okay, so actually, I mean, probably the closest example is BEC, right? We know that in the BEC, for the gas to thermalize, you have to have like 2 or 3 collisions at least, right? So gravitational interaction is so weak that basically on these scales, there is no thermalization at all, okay? But there is so-called virialization, okay? So, and basically, remember from the classical mechanics, right, for a classical system to be stable, right, you have to have a certain balance between kinetic and potential energy, okay? So, and essentially this is the case, okay, of this system. So there is no thermalization in the regular sense, but there is a realization that also leads to this quite distribution. I hope I answered the question, right? So, but the important point, okay, so that I wanted to make, okay, so so that this range of masses, okay, it is complementary to what is being done in particle detectors. Okay, this is an enormously important point. Okay, we are trying to cover the parameter space that is completely different. Okay, so and remember that philosophical argument about the complexity of dark matter. Who knows, right? The WIMPs, as we have heard several times already, I mean, they could run into the background, you know, in the next few years and then what, right? So this provides an additional window into what the dark matter could be. Okay, so we have this ongoing search for topological dark matter with GPS. Okay, so the essential idea here is that we have this network of satellites, and satellites have atomic clocks on board. Okay, and we are looking at glitches propagating through this network at 600 kilometers per second. So this is that galactic velocity that I was talking about before. Okay, so and I'm selling this as a 50,000 kilometer dark matter detector. So essentially, this is a dark matter detector that has been already built. Okay, so it is so. Essentially, what we are doing, we are analyzing about 10 years of data, data mining them, and trying to find out if there is this signal propagating at 600 kilometers per second. Okay. So, and of course, I mean, the investment, the money that we are spending on this is orders and orders and orders and orders of magnitude smaller than LHC, right? Again.
How does this compare with, let's say, aluminum and a mercury clock at Boulder? There's just 2 of them, and they're not moving, and they're in the same place, but they're
so it's a different regime. So I would need another another minute. Yeah. Okay. So, but this is our team. Yeah. So, and we acknowledge this support from the National Science Foundation. Thank you very much, Michael. Yeah. So, and then okay, and most of the work, of the hard work, is actually done by Ben Roberts, who is a postdoc. I'm going to show some of the results that we have recently obtained. Okay, so so this is a typical GPS data stream. Okay, so atomic clocks, and basically these are the clocks. So I mean, these are different satellites. Okay, and then we have the clock phases in nanoseconds. So it's essentially this is a clock reading on board of the satellite. So so each point that we have is a 30-second. So the rate of sampling is 30 seconds. Yeah. So about 10 years of data. So the maximum number of satellites that we have in the constellation is 32. So and then there is also a number of ground stations with H masers and other clocks. Okay. So and then so what is the signal that we expect? Okay. So suppose I just have two clocks. Okay. So and this is that. So I and initially he just looked at the topological defects in the form of thin walls. Okay. So when the wall comes through, it pulls on the frequencies of the clocks. Okay. So you are expecting a spike like that, and then when it overlaps with the second clock, is typically our reference clock. Okay. The spike goes down. So the plus and minus sign is because I'm looking at the difference in clock frequencies. Okay. So now, how long does it take for a topological defect to fly through this network? It's easy to estimate. So it is the diameter of GPS installation is 50,000 kilometers. I take 50,000 kilometers, divide by 600 kilometers per second, and I get about 150 seconds. Okay, so 150 seconds is a lot. Okay, so now how does it map into the data? Okay, so so you have a network. Okay, and moreover, what you have is not the frequency measurement. Okay, it is the phase measurement of the clock. And also we have this phase measurements every 30 seconds, okay? And then you could map this system into this discrete representation of the network. So the boundaries here are the time steps, okay, that we have, and the 0 here is a reference clock, right? So it is this clock here. And you could see that there is a certain pattern that we should see. Okay, so the red tile here is this spike, and it happens when the defect hits the clock number 1, and so on, right? And also we know the direction of the galactic motion. In fact, it goes through so we are flying towards the Cygnus constellation. Okay. So and at least yesterday, that direction in the morning it was over the right where Mark sits. Maybe it's a good sign, right, Mark? Okay. So at least, but that direction changes over time, right? And then we actually have to rearrange these tiles in such a way that the sequence of events it happens in a certain way. Okay. So and then this maps the data that we have into an image recognition problem. Okay, and that is what we have done. So and essentially this is our current result. Okay, so this is a constraint on the coupling strength. Okay, so these are the previous constraints coming from laboratory and astrophysical data, and you could see that we are improving even with GPS. Okay, we are improving these constraints by several orders of magnitude. Okay, there is an interesting region here, okay? Remember that GPS is operated by the military, okay? So, and the military, it turns out, it adjusts the timing of the servo loop all the time, okay? So, and there is a certain range, and we don't know what the constant on a specific satellite is. And this introduces uncertainty in terms of the size of the wall that we can detect. Okay, so but nevertheless, I mean, so I mean, you could see that his constraints are quite amazing, at least to me, you know, already at this point. So, and you have not explored actually, you have not pushed this technique all the way through. So the next step that we are doing is a Bayesian statistics analysis, and I'm not going to talk about this much, but basically here are some results of a Monte Carlo simulation by Ben. Okay, and this peak here, it corresponds to a signal which is just 0.5 sigma event, okay, and the relative odds ratio is 10 to 1. So it's easy to actually to see in data, although the signal itself could be buried in the noise. With the Bayesian statistics technique, you could pull out a lot of information that is hidden. Okay, so, and that is going to be our next step. Okay, now how much time do I have left? About
15 minutes until questions.
Okay, now I'm going to switch to a different topic now. Okay, so I was just talking about topological defects that come from self-interacting dark matter. Okay, now I'm going to I'm going to flash this view graph again. Okay, that is what we know about dark matter, right? So, and then I'm going to consider a different model. So, since this field is at the very beginning of this development, I could come up with abbreviations that I like. Okay, so and okay, I'm going to call this his fields as VULFs. Okay, because you need a catchy name, right? Okay, so I mean, what people are using now is a mouthful. Okay, so and what are these guys? Okay, so these are going to be the scalar bosonic fields. Okay, so the spin is going to be 0. Of course, these are electrically neutral because this dark matter candidate is not supposed to interact with the electromagnetic field, right? Okay, so and quantum field theory tells us that then this particle is going to be its own antiparticle. So these fields are a generic prediction of many extensions to the standard model, including string theory, where these guys are referred as dilatons. Okay, so of course, I mean that gravitational interaction is a given, so I'm not going to include any self-interaction, and I will assume that these particles are distributed according to the quasi-Maxwellian distribution, as I have shown already. Okay, so this is the atomic physics community, so I have to probably introduce what Klein-Gordon equation, or remind you what the Klein-Gordon equation is, right? So, okay, so it looks like this. It is a relativistic equation. Okay, so and it is for the bosons of spin 0. So, and you could immediately check that the solution of this wave equation are, of course, plane waves. Okay, so the phi naught here is an amplitude. Okay, and you could compute the energy density associated with this field and connect it to the dark matter energy density that I told you already about. That 0.4 GeV per cubic centimeter. Okay, so and this amplitude also depends on the mass of the particle. Okay, so now the frequency of the oscillations is given by this relativistic expression, right? So it's the rest mass and kinetic energy. So you could make an expansion, and you could see that the leading term is just the Compton frequency, so it is the rest, so associated with the rest mass of this particle. And the second piece depends on the velocity, and this is going to do two things. Okay, the first thing is this our galactic motion, so it's going to lead to the Doppler shift. Okay, and the second effect is going to be broadening because we have the velocity distribution. Okay.
Why do you pick the cosine and not each with the I solution?
You see these dots here? Okay. Ah, why it is a cosine? Because it is a scalar field, and it must be. This is it. Okay. So, I mean, the quantum field theory tells us that that must be real. Okay.
And I superimpose cosine and sine. Why does it need to be real? Sorry, maybe this is a silly question.
No, it's there is some. Okay, I have to look it up, but we could talk
Okay.
about this later. But it is a theorem, in quantum field theory, it is the theorem is that if you have s equals 0 and electrically neutral, then the field must be real. Okay, there is a theorem like that. I don't remember the proof of it, right? Okay, and I guess you don't expect this proof anyway. Okay. So, okay, now, all right, now you have these fields that are oscillating, okay? So, and they're oscillating at the Compton frequency, and now you could look at this parameter space. So it's, what, 24 orders of magnitude in mass, okay? So, from 10 to the minus 24 to 1, okay? And this 1 EV it comes from the requirement that these fields are coherent on the scale of an individual detector. Okay, or actually, I mean, the statement is even more precise. If I tell you that I require that the number of particles per de Broglie volume is much greater than 1, then I could talk about this Wilson setting up coherently, and then on the scale of an individual detector, you have well, almost a classical field. Okay, so and you could see now our experimental friends, should appreciate this range, right? So essentially, this is one oscillation per year, and the 1 EV it goes to all the way to optical frequencies. Okay, so it's enormous range of frequencies. Okay, now let me also look at the spatial dependence, right? So now you have this k dot r, right? In the reference frame of dark matter Halo, the average value is 0, of course, right? But if I'm in the solar reference frame, I'm flying through this distribution of velocities, right? And then the average value is going to be this galactic wave vector. So it is m phi times the galactic velocity divided by the h bar. Okay, now, so let's talk about couplings a little bit. Okay, so, and I'm going to be super generic here. Okay, so, and what is typically happening in our community, right? People are talking about portals. Okay, so, and I'm just going to look at the linear portal. So, and the linear portal is basically taking pieces from the standard model Lagrangian and multiplying them by the field. Okay, so and lambda x here is the energy scale. Okay, so essentially it parameterizes the coupling constant. And what happens here is that the masses and other fundamental constants like the fine structure constant, okay, they are getting denormalized by this field. Okay, so now you have both spatial and time dependence of fundamental constants. Okay, so and remember the field here it oscillates, right? So essentially you have oscillating masses and oscillating alpha and oscillating strong coupling constants, etc. Okay, so And this is a different regime, of course, compared to what people have looked at NIST, right? So, okay, it's your question. Okay, so it is a new regime. So, the first example, this GPS search that I have given you, it was a regime when we are testing for the transient variation evolve. Okay, this is a different regime where we are testing for the oscillating variation evolve. And moreover, there is even more here, right? Because it's not only the time dependence that matters, but also the spatial dependence. Okay, now, as I told you, this field had a lot of activity over the past 2 years. There were many proposals, and I probably have not listed well, all the proposals, but at least the ones that I have looked at, and people have talked about atomic laws, magnetometers, accelerometers, interferometers, etc. Okay, so in fact there is a huge range of possibilities of what to couple to and what to search for. Okay, so this is one of the examples. So Mark has shown a similar plot, but he hasn't shown ours, so I decided to show our plot too, right? So anyway, so this is a typical plot. Okay, so essentially what you need to look for is a parameter space that is not constrained yet. Okay, because, for example, in terms of atom interferometry, right, there is already a region that has been excluded by the static equivalence principle test, right? And now, if you run your apparatus, you have to actually look at the parameter space that hasn't been excluded yet. Okay. So, and what could happen? Either you find that oscillating signal, which is great, right? So, or you constrain this plot even further. Okay. So this is how this works. Okay. So and now the point that I would like to make, and I'm quickly running out of time, right? So is that in fact, okay, so far all these proposals they've been talking about oscillating at a specific location, okay? But in general, I still have 5 minutes. That's great, okay? So, but in general, this is much deeper than just oscillations at the Compton frequencies. These are waves, okay? So, and now if I'm looking at the relation of the signal here and there, okay, there is a certain phase relation, okay, and this is much, so it provides extra confidence in your signal, okay. So, and what I have plotted here are different labs, okay, high precision measurements labs around the globe, okay. So there is one on the South Pole. This is my Chromatis experiment. Okay, so there are plenty of labs in Europe, in Japan. There are some labs in China. Okay, so and of course US as well represented here, and there is one point even in Australia. This is Mike Tober, right? So now. This comes actually, this idea is partially motivated by the Welker network that he is establishing his optical magnetometers, and we are going to hear about that network in the next talk. Okay, so, and basically the idea is that you could have a much better statistical sensitivity than that of an individual device, and definitely the scaling is going to be better than 1 over square root of m. M is the number of nodes in this network. Okay, so then I talked about different portals, right? But you actually don't know which portal is going to work. Okay, so if you have a wider network of these tools, then you could actually you could cover much wider range of possibilities. And of course, it could be built on the backbone of known, right? So, and what is needed for a network like that are synchronized measurement. And essentially, known, I think, sells a box for about $1,000, right? So where $3,000, right? Where you could data stamp your data acquisition. Okay. So and we had the I got to put a reference here. So D. Mabutker and I we had a little letter in Physics Today which argues for this type of measurements. Yeah? So, and of course, I mean, our own network GPS, it can be also used for to search for these waves. Okay, so I'm going to skip most of this. Okay, so it is a theoretical construct, you know, two-point correlation function. But the point is that you could actually derive, you know, what the correlation function between two nodes of a network could be. Okay, so and if you have a correlation function. So, alright, anyways, I mean, I've done some analytical work, so you could actually encode all the priors on dark matter distribution, including velocity distribution, galactic motion, and everything like that, and that goes into this correlation function, okay? So, actually it was a fun little exercise. I just went to the books on quantum optics and rephrased everything about photons in those books, but just upgraded that to the scalar massive bosons. Okay, so and the correlation function here is essentially G1 that occurs in quantum optics textbooks. Okay, so and if you have a correlation function, I think this is actually what could be of most interest now to the experiments that are ongoing. You could derive a dark matter line profile. Okay? So, I mean, you have a correlation function, you take the Fourier transform, and this is how it looks. Okay? And it looks weird. Okay? So zero here is the Compton frequency, right? Okay? But then the dispersion relation for these bosons is such that the kinetic energy piece is always positive. So you are adding stuff, okay? So, and that's why the line is strongly asymmetric. And then also there is a Doppler shift associated with the galactic motion and all of that. So, I mean, there is an analytical expression time, right? Okay, so, right. And just a few ideas, okay? So you could also probe the correlation function with satellites, so Mark, and also we had a talk from Ron and you, right? So, and you could probe, in fact, the correlation function by using the satellites of the space mission, right? So this is the Cygnus constellation I was talking about, okay? So, and then you could change, for example, the distance between the satellites and probe the correlation function that way. So, or on the Earth, okay, the correlation function itself, it depends on the dot product of the galactic wave vector with D, okay? So, the Earth is going to spin around, okay? So, the dot product is going to change over time, and then you could also probe the correlation function that way as well, okay? So, and this is it, okay? So, I think at least on the experimental side, this is the most relevant result at the moment, okay? So, and if you see an oscillation and it has a profile like that, then you could argue that maybe you have seen dark matter, right? Okay? So, all right.
So in view of the coffee break, I will keep the number of questions down a little bit. So I don't know. Jeff.
Yeah, going back to your first topic, the light dark matter search with
Yes, absolutely. Absolutely, right. So in fact, I mean, our most advanced analysis is based on the Bayesian statistics. Okay. So and
statistic, I mean, gee, George.
huh?
Just doing fancier statistics.
No. It's much more deeper than that. Okay. So it turns out, you know, I mean, to my big surprise, that most of people in atomic physics community don't care about Bayesian statistics. Okay. So. And it might be a good thing, it might be a bad thing, but nevertheless, I mean, Bayesian statistics, it provides you this very, very systematic way of approaching your claims, right? Okay. So there is one. So let me actually go back to the data. Okay. So the data itself. Wait. Okay, so it's okay. So the systematic error. Okay, that so okay. First of all, the question number one that one has to address: is there any other effect that could propagate through a network at 300 kilometers per second? That is our signature, right? And the answer is most of the effect don't. But there is one effect associated with the solar wind that can propagate at 300 kilometers per second. Okay? So, but that effect, it comes only, so it is highly directional. So it comes from the direction of the sun, of course, right? And we could exclude it. Because actually we are looking at a certain direction associated with galactic motion. Okay? So this is in terms of systematics, right? Then, so now if you are thinking about how so the next systematic effect is not associated directly with the galactic motion. It is actually the GPS data acquisition and analysis, right? So, and what is happening there is that there is an error bar associated with this, okay? And these error bars are, in fact, coming from uncertainties of the model. So we have to connect the phase measurements of these microwaves, so L1 and L2 and L5 bands, okay, that come down, and then those phase measurements have to go back to get this strip, right? And the formal error bar is in fact associated with the modeling of the ionosphere and all of that, okay? And we don't do this part actually. It is done at the GPL. They have, so this is a different community. It is the geosciences community that does this, okay? So, and one of our collaborators is in fact one of the original developers of that code that takes the data and puts it into, okay? So, and that is that error bar, right? So, in fact, I mean, the result that I have shown, okay, it is at the level of about 5 sigma. Sigma is the error bar here, okay? So, we have not gone all the way down, okay? So, this is just the first results of this analysis, okay? So, then you have to do the Bayesian statistics because, in fact, what is happening here, it is essentially trying to dig out a transient signal out of this sea of data that is noisy, okay? And in fact, I could give a completely different talk about this. I mean, I could talk maybe one-on-one, you know, but nevertheless, I mean, it's a very powerful technique, okay? So, and I have shown just one of the examples of what is happening in our Monte Carlo simulations, and we can really pull out a signal out of this noisy background because we are looking at certain transient signal at a certain velocity, at a certain direction. So it is possible with high degree of probability. Okay. So, all right. Anyways, I hope I at least partially have answered that question. Yeah.
So, in view of the fact that we are already 10 minutes in the coffee break, I would say let's have a coffee break. Let's be back in 10 minutes. The talk is not Victor Flamboun's, but Andrew. And thank you again, Andrei.